Hello everyone, I'm David Aksun, final year PhD student in EPFL. Today, I will be talking about evaluation of in-cache line logging with Intel Optane persistent memory. The work that I'm presenting today is not previously published. Earlier version of this work was published in ASPROS 2019 in collaboration with Nahshon Cohen, Hira and James Larus. This talk builds on that work. I will refer to the entire idea shortly as in-cache line logging. I would like to extend my gratitude to Intel for providing me with the opportunity to access their servers equipped with Intel Optane. So, what is the practical application for persistent memory? Persistent memory is fast, has high capacity, and is byte addressable. It can take an existing data structure and store it in persistent memory. Then we can operate on the data structure that is stored in the persistent memory directly. However, the processor caches are volatile, and if a power failure occurs, the data structure can be in an inconsistent state after recovery. We need to add a crash consistency mechanism to the data structure for correct recovery after restart. We had a good idea to build fast durable data structures. We provided in-cache line logging as a crash consistency mechanism for building durable data structures. In-cache line logging is an approach for an expert library developer to build durable data structures by avoiding explicit cache line writebacks in the fast path of the application. The data structure completely resides in the persistent memory, and the in-cache line approach provides crash consistency for the data structure. We published in-cache line logging in ASPROS, and we were proud of the contributions in our work. While working on the project, we didn't have access to any Optane devices. Similar to the previously published works, we used software simulation to evaluate the in-cache line logging idea. Later, we had access to the real Intel Optane persistent memory devices. We went back and revisited our idea by using the real hardware for evaluation. We reran our experiments on the real machine, and the results were surprisingly different. This talk is about why our measurements are different when running the experiments on Optane, and why our reasoning at the time seemed plausible. Optane devices are great, and we have waited so long for these devices to come to the scene. However, Optane in its current form is still slower and has limited bandwidth compared to DRAM. There is a well-known saying, you get what you measure. In our simulation, we allowed delays to be introduced after an S-fence operation to model the cost of cache line flashes. Other papers also use the same simulation technique. We built an implementation that optimized the number of flashes, which is what the simulation focused on. However, our implementation put the data structure in persistent memory, so we did a large number of reads and writes to the persistent memory, which had elevated costs when running on Optane. As researchers, we should be open to reconsider our previously published ideas and talk about their feasibility. Optane devices will be faster in the future and will improve in many ways. However, Optane, in its current form, is already being deployed in data centers and is commercially available. In this talk, I'm taking in-cache line logging as a substitute for any crash consistency mechanism that does a lot of reads and writes to persistent memory. We believe that putting a data structure on Optane and directly accessing the data structure is not a good idea, because the application has to pay the cost of accessing the data structure on Optane. On top of this cost, the application also has to pay an extra performance overhead coming from the crash consistency mechanism. In the Aspros paper, we reported the overhead of adding the Incll-Optane crash consistency mechanism to the Masstree data structure. The reported overheads varied between 6 to 15% across YCSB workloads without any delay. We also reported the change in throughput when we introduced additional delays after an advance operation to model the effect of cache line crashes. For YCSB-A, even with an added latency of 1 microsecond, the performance of in-cache line logging decreased by 4% for the uniform workload and 6% for the Zipf-in workload. To sum up, the overhead of in-cache line logging was reasonably low, and we had an implementation that was optimized for cache line crashes. For this talk, I'm using the Masstree data structure for evaluation, which is a combination of B plus 3 and try. The figure presents the throughput of write-intensive YCSB workloads for both baseline Masstree and in-cache line logging approach. We use uniform access pattern to model random accesses and Zipf-in to model popular key accesses. There are 20 million initial keys and the operations are done by 8 worker threads. In the figure, we have baseline Masstree and the in-cache line logging approach. The y-axis depicts the throughput. In-cache line logging has the highest overhead in YCSB-A write-intensive workloads, as modifications use in-cache line logging extensively. In the figure, the slowdown of in-cache line logging is 15% for the uniform workload and 10% for the Zipf-in workload. Those similar overheads also hold for real hardware. Now, we can talk about the results in a completely different machine, which is equipped with Optane. How does Optane have an effect on the results? For now, let's focus on the YCSB-A write-intensive results, where the overhead of in-cache line logging is the greatest. Any figure presented from onwards will not have any added latencies. The y-axis shows the throughput of in-cache line logging normalized to baseline Masstree. In the figure that I'm presenting, for both baseline Masstree and in-cache line logging, the allocations for the node structures and the value buffers are done over an emmapped region. The node structures and the value buffers of Masstree can either be in Optane or DRAM. So, baseline Masstree can either use Optane or DRAM. Before delving into the Optane measurements, I want to pose a few questions to the viewer. Which device did we use to place the node structures and the value buffers of Masstree for this figure? Does the baseline Masstree use DRAM or Optane for node and value buffer placement? Similarly, does in-cache line logging use DRAM or Optane for node and value buffer placement? Try to guess it. If you guessed DRAM for both, congratulations. I assume it was not a hard guess. The slowdown of in-cache line logging is 18% for the uniform access pattern and 17% for the Zipf-in access pattern. The current machine is different compared to the one used in Aspros. However, the results are within the expected performance range. Now, I'm presenting a similar figure compared to the one from the previous slide. The only difference is the placement. Instead of making you guess, let me tell you that both baseline Masstree and in-cache line logging use Optane. The slowdown of in-cache line logging is 18% for the uniform access pattern and 20% for the Zipf-in access pattern. The results are very similar to the previous figure's pattern, with a minor performance degradation in Zipf-in. The overhead of in-cache line logging is almost insensitive to Optane placement. It seems in-cache line logging maintains a similar throughput degradation when used with Optane. The results were consistently on Optane. So we can just investigate the overheads in detail and optimize the work as much as possible for the new Optane device. Later, after everything is perfect, we can apply the idea across many more data structures and data center applications, and we can deploy it. So are we almost done? As expected, I wouldn't be giving the talk if these two figures were sufficient by itself. But if we ask a simple question, what is the overhead of using in-cache line logging running on Optane compared to baseline Masstree running on DRAM? I'm again presenting a similar figure to the one used in the previous slide. The only difference is the placement. As you can see, the gap is huge, and from a runtime performance perspective, almost irreconcilable. The slowdown of in-cache line logging is 64% for the uniform access pattern and 51% for the Zipf access pattern. If we just report the slowdown with respect to Optane placement, the overhead of introducing in-cache line logging is not much, and in-cache line logging is mostly insensitive. However, if we compare DRAM measurements with Optane measurements, we get an entirely different picture. The reason this figure is important is due to the opportunity cost of not using DRAM. In-cache line logging requires the data structure to be in the persistent memory, and all the updates to the data structure has to be in place updates. By using in-cache line logging, we are paying the cost of using the crash consistency mechanism. By using Optane, we are paying the cost of having an impersistent memory data structure. Here, we can see that the majority of the cost is from using Optane. Let's forget about in-cache line logging for a second and consider baseline Masstree. What is the cost of persisting baseline Masstree on Optane? The red bar represents the normalized throughput for storing the nodes and the value buffers in Optane for baseline Masstree. The slowdown of Masstree on Optane is 56% for the uniform access pattern and 38% for the Zipf access pattern. Zipf workload can perform better due to locality. However, there is a huge performance hit when using Optane only. The main message of the figure is that Masstree executes much slower when running on Optane compared to DRAM. Let's investigate the effects of using Optane further by examining the program under Vtune for baseline Masstree running on DRAM and on Optane for the YCSP-A uniform workload. I'm presenting the measurements from a portion of the workload execution. In general, the increase in CPU time is due to memory accesses. The figures on the left and the right depict the top 4 functions that consume CPU time for both DRAM and Optane cases. For example, the compare function, which does key comparison, or the row is marker function, which reads the timestamp from the value buffer, take more time than running on Optane. Masstree has optimistic concurrency for reads and uses locks for writes. The locks are implemented within the node structure in a single fashion. The majority of the overhead comes from the stable annotated function, which is used to read a stable version value for a given node. The stable annotated function can lead to a spin loop as well. The function is also frequently called in the traversal part of Masstree and heavily relies on access to memory. In the measure portion of the execution, the bandwidth measurements clearly indicate the bottleneck. The write bandwidth of Optane is between half and a quarter of DRAM bandwidth, while the read bandwidth is almost a half of DRAM bandwidth. The main bottleneck is using Optane. In the rest of the talk, I will provide more evaluation for the in-cache line logging idea running on Optane. However, first, I will provide an overview of the in-cache line logging idea and how the idea fits well with the simulation evaluation approach to better understand the results and to reason about the overheads. Then I will provide the rest of the evaluation and investigate how the slowness of Optane imposes constraints for design ideas that operate directly on the data structure stored in persistent memory. We also implemented a solution that addresses the weaknesses of the in-cache line logging idea, which also takes the bandwidth limitations of Optane into account. However, I will leave the solution for another talk. I will now present the in-cache line logging idea. In-cache line logging idea is a method to be used as a tool for expert library builders. In-cache line logging addresses both the weaknesses of traditional checkpointing and transactional undo logging. In-cache line logging consists of two components. The first one is fine-grained checkpointing, which relies on the periodic persistence idea from the Berry hash map. The second one is using a log within a cache line, which is the nowhere contribution. Using both components, each in-cache line logging can achieve zero explicit writebacks in the fast path of the data structure. In-cache line logging divides the program execution into fine-grained epochs of 64 milliseconds. At the start of an epoch, checkpointing persists the entire cache hierarchy using writeback invalidate instruction. Checkpointing leads to 5.8% overhead in Optane. For checkpointing, there is not a separate copy of the data structure to buffer the modifications. The data structure is stored directly in the persistent memory. Persisting the entire cache hierarchy at the end of an epoch ensures that all the modifications to the data structure will be propagated from the caches to the durable data structure stored in the persistent memory. That is why, if a power failure occurs during an epoch, the application needs to roll back the modifications done in a crashed epoch. Unlike traditional checkpointing, which relies on keeping track of 30 pages, we can use an undo log to roll back the state. The undo log has to be in persistent memory too. The time spent on checkpointing is bounded by the number of 30 cache lines, which is bounded by the cache size. Fine-grained checkpointing is sufficient when combined with an undo log. However, it does not lead to optimal runtime performance. The problem is the undo log. Any in-place update has to be preceded by a call to the undo log to save the old value. For crash consistency, undo log has to be consistent before any update to the data structure. To provide crash consistency, undo logging relies on expensive explicit cache line writebacks. For x86, explicit cache line writebacks usually involve cache line fresh instructions followed by a fence. Using explicit cache line writebacks, the undo log can flash the dirty cache lines that need to be persistent and be in a consistent state. The writebacks require a full memory round trip time, and modifications are usually done in the fast path of the application. Waiting for persistent memory in the fast path of the application can lead to performance degradation. Even if you all know how logging works, let me quickly demonstrate how traditional undo logging works, in this case to modify the in-cache line logging idea. I will use the values array of a B+3 node, which fits a single cache line. The application has to log the old value and then later modify the data structure. In the example, the application generates a log entry with value 7. After creating the log, it is necessary to write back the dirty cache lines of the log for crash consistency. This operation makes the log entry visible in the persistent memory. In the example, the log entry containing the value 7 for key 5 is made visible in the persistent memory. Finally, the application can continue mutating the data structure. In the example, the value 7 for key 5 is replaced with value 6. In cache line logging idea eliminates the explicit cache line writebacks from the fast path of the application. Instead of having an external undo log, the idea for the in-cache line logging is to simply put the log inside the cache line that is being modified and avoid waiting for a full persistent memory round trip time. For example, in-cache line log can be a word of 8 bytes stolen from the end of the cache line. Instead of using an external log, in-cache line log uses the stored space for logging the value. The new algorithm is as follows. The value is logged to the in-cache line log. In the example, the value 7 for key 5 is stored in the in-cache line log. The application then continues mutating the data structure. In the example, the value 7 is replaced with value 6. The main reason that in-cache line logging can avoid explicit cache line writebacks in the fast path is that the modification is done to the same cache line. The only requirement for the application is to ensure that the in-cache line log is validly written before doing a modification to the data structure. The ordering of writes can be done using a release fence, which introduces a happens before relation between the writes and has no cost on x86 architecture. There are two possible states that a cache line can be in the persistent memory at the time of power failure. The first possible state is that the modifications are not propagated to the persistent memory, so the state of the cache line in the persistent memory has not changed. Therefore, recovery is unnecessary after a power failure. For example, the value of key 5 is not modified, and it has the same value in the beginning of the state. The second possible state is that the modifications get propagated to the persistent memory. After power failure, the application can use the in-cache line log to restore the state of the cache line back to the initial value in the epoch. For the example case, since key 5's value is 7, is already logged in the in-cache line log, the application can roll back the value of 7. The main issue for using an in-cache line log is the size of the log. Not all the operations done to a cache line can be stored within the in-cache line log. Let's look at the example. We want to do more put operations to other locations within the cache line. The in-cache line log does not have the capacity to keep track of all the changes. One possible solution is to increase the size of the in-cache line log, which consumes space within a cache line and can alter the characteristics of the application significantly. Since our design uses periodic checkpoints, we can fall back to using an external undo log. For operations that cannot be covered by the in-cache line log, the crash consistency mechanism falls back to using an external undo log. The external undo log uses node granularity for logging. If an in-cache line log is not sufficient to keep track of multiple modifications, the entire node is logged using an external undo log. In the example, the node is logged entirely. The main benefit of node granularity is that all the succeeding operations within the epoch to the node do not need to be logged, as the log entry for the node contains sufficient information for recovery. However, using the external undo log has a cost. You still have to pay the cost of logging the node once per epoch. Sum up, in-cache line logging idea can support zero explicit cache line writebacks in the fast path of the data structure. Avoiding waiting for a full memory round trip time is very useful, even for evaluation under Optane. In-cache line logging is a good tool to have when working on software for persistent memory to improve runtime performance. The main issue is the placement cost of using Optane. In-cache line logging idea is heavily dependent on using persistent memory, as the crash consistency mechanism supports in-place updates. Any data structure using in-cache line logging has to be on Optane. On top of this, the external undo log is also on Optane. However, Optane is slow. Therefore, the throughput degradation due to Optane will be the main bottleneck, which is unavoidable. These are the settings of the server equipped with Optane, which we use for evaluation. We evaluate the system on a single socket by pinning the threads and disabling the turbo boost. Setting up the system to use NVM is quite straightforward. We use IP-MCTR to set the AppDirect mode. We use NDCTR to create the persistent memory device, interleaving 6 NVDIMMs for a socket. Then we install a file system and use the direct access feature to avoid using the page cache and access persistent memory directly using rows and stores. For the rest of the evaluation, I will keep the same style by presenting two versions of Masstree, where the placement can either be on DRAM or Optane. For evaluation, we use YCSP workloads with uniform and Zipf distributions. The current evaluation does not use any artificial latencies. Unless stated otherwise, we use 20 million keys to pre-populate the data structure and 8 worker threads to perform the operations. Now, I'm going to present different YCSP workflows. First, I will show the YCSP-A in a more compact way. As we have seen before, the slowdown of in-cache line logging with Optane is 51% to 64%, as shown in the red bars. Sadly, the upfront cost of using Optane already leads to 38 to 56% slowdown, as shown in the green bars. YCSP-A is write intensive, which does 50% writes and 50% reads. So, what happens if we reduce the rate of writes? Do we also pay a cost for using Optane in read-only workflows? The answer is sadly yes. Now I'm going to show a read-only workload figure. The figure presents the YCSP-C workloads, which does 100% reads. The upfront cost of using Optane for baseline Masstree is 26 to 46%, as shown in the green bars. While the Zipf workload has better locality, just doing reads lead to almost 50% cost for the uniform case. This is baseline Masstree, so there is no logging, there are no cache line flushes, there is no crash consistency mechanism. However, still the application has to pay an enormous cost for even read-only workloads. In-cache line logging has an inherent cost due to changes in the cache line design and periodic checkpoints, which is unavoidable. So adding in-cache line logging on top of the baseline Masstree further introduces an extra cost as well. The slowdown of using in-cache line logging with Optane is 36 to 54%, as shown in the red bars. Again, in a read-only workload, the in-cache line log is not used and the cost of using Optane is great. For the cost of using Optane, we expect similar behavior compared to the previous slides, two previous slides, if you mix read and write. Now I'm going to show YCSP-B, which is sort of a mix of both YCSP-A and YCSP-C. YCSP-B is read intensive, but also does writes, which is 5% writes and 95% reads. We expect the slowdown to be impacted mostly by Optane, and as expected, the cost of using Optane is 27 to 48%, as shown in the green bar. When we add the in-cache line logging on top of baseline Masstree, the slowdown increases to 38 to 56%, as shown in the red bars. We can see the limitations for both the write and the read bandwidth in YCSP-A-B-C experiments. The cost of accessing persistent memory dominates the cost of using the crash consistency mechanism. Accessing the data structure directly stored in persistent memory is not feasible. We can look at the YCSP-E experiments and observe that the same principle still holds. YCSP does a lot of scan operations, which is 95% of all operations, and does a small amount of write, which is 5% of all operations. In Masstree, the scan operations are slower compared to normal and read and write, and return a range of values. We can see by looking at the green bars that the overhead of using Optane for the baseline Masstree is 21 to 36%, which is still a lot just for using Optane. We want to see the scalability of just using Optane and observe the limits of the bandwidth that can be imposed by the underlying memory. Therefore, we increase the number of threads and examine the throughput. The figure shows the scalability of baseline Masstree approach on Optane machine using YCSP-A uniform workload At 24 threads, the performance slowdown of baseline Masstree with Optane increases up to 67%, as shown in the red bars. Again, there is no added crash consistency mechanism, and the overhead is just enormous. When we add crash consistency mechanism, we get a further slowdown, which increases the slowdown up to 73% for in-cache logging using Optane for 24 threads. The limitations in the bandwidth of Optane has a degrading effect for the scalability of the data structure. By just placing the data structure on Optane, we severely impose throughput limitations. Optane is a slower device with a lower read-write bandwidth compared to DRAM. The measurements done using Optane are not the end of the work. Technology keeps improving, and we hope that Optane's bandwidth will improve in the future. However, the limitations on the read and write bandwidth of Optane are critical for runtime performance. So avoid operating on data structures directly in persistent memory, as it is not a good idea at the moment. Throughout the talk, we showed how optimizing for simulation can be misleading, as it can lead to optimizations that favor the simulation. The characteristics of the simulation can ignore the important characteristics of the real hardware. For your questions, you can contact me in the given email address below. Thank you for listening.